Hello everyone, in this video I will show how you can solve differential equations in Mathematica. We have these two differential equations. We'll solve one by one and then I will plot some of the curves from the family of solutions to this differential equation for some constant values c1 equals to -2, -1, 0, 1 and 2. Let's solve the first one. So to solve differential equation you will have to write d solve with capital D. And in the square bracket write the expression xy prime minus y double equal sign x squared sin x, and then give a comma and write the unknown is y of x and the parameter is x. You can see in this equation we are taking derivative of y with respect to x. So every time y appears in this equation, you'll have to write y of x. You cannot keep y alone. So x y prime of x, so you'll have to give square bracket and write x inside, minus y of x, and also in the unknown you'll have to write y of x. So if you press shift enter now, it will take some time. So this is the solution. X c1 is a constant minus x cos x. If you don't write y of x and keep y alone, Mathematica will not give you the solution. So every time y appears, you'll have to write y of x. Now we have the solution. Now you can just substitute the values of c1 and plot them. We will have a graph for each of these values. So in total, we will have 5 solutions in the graph for these 5 constant values. Now I will not copy paste the solution. I will just write y of x and then give replace sign, and I will write percent sign. Percent sign means the last output. So if you press shift enter now, it will show me just the last output, which is xc1 minus x cos x. But as the last output keeps changing, it won't work if you press shift enter again. So it's better to use specific output cell number. As you can see that the solution is in output cell 3. You can just write %3 and Mathematica will take the output from output cell number 3. So here % means the output and 3 means the cell number. So %3 means the cell number from output cell 3. Now I also want to replace this c1. This c1 is basically capital C and 1 inside the square bracket. You can see that this is the c1, but I want to replace this with an ordinary alphabet. So use replace sign and capital C and 1 inside the square bracket. I'll change this with say a small a. I have changed this because it's difficult to work with that c1. So now I have a in the expression. Now let's save this expression in the solve variable. You can use any other variable, and I will use this variable to plot all the solutions. Now I will use table function to make a list of these 5 solutions for a equals to -2 to 2. So use table, and inside the table just write the expression solve, and I want to vary a from -2 to 2. If you press shift enter now, you can see that I have a list with 5 of these with a equals to -2, -1, 0, 1 and 2. You can also specify the increment. As you can see, the increment here is 1, -2 to -1, and if you want the increment as half, you can specify that. So we'll have 10 values then with increment half, -2 to 3, -3 by 2 and then -1. But if you don't mention an increment, Mathematica will take increment 1 by default. So we need the increment 1 in our case, so we'll keep that. Now how do you plot multiple functions? We write a list of functions like x squared twice x inside plot command. But here using table function, we have already generated that list. Now we can keep that list inside plot command and then specify the range of x to plot all these functions. So I'm keeping the list inside the plot function, and then I'll give a comma and specify the range of x. Say I want to take x from -5 to 5, and if I press shift enter now, I'll see all the curves. Now there are 5 different curves here, but it's hard to differentiate among them as they are all in blue. So I'll keep the whole list inside evaluate function to see them in different colors. Also, you can use plot legends to see which function is which. So now you will be able to tell which one is which from the graph. So this way you can plot family of solutions for 5 different constants. C1 equals to these 5 constants. So we have solved the first differential equation, that was y prime. Now solve the second one. The second one does not have y prime. It has dx and dy separately. So how do you solve this in Mathematica? So let's delete all these cells and also delete the variables. Go to evaluation and select quit kernel and select local. All the variables will be cleared. Now to solve the second one, again write dissolve command, and inside dissolve write the expression x cubed plus y cubed. So y is the unknown, so you cannot write y cubed, you have to write y of x cubed. Y of x is a built-in function, so y of x cubed minus y. Well, there is no y of x in the second one, so x cubed plus y cubed dx. So how to write dx? So to write total derivative dx, write capital D and small t and write x inside the square bracket. So this way you write dx. Then plus 3x y of x squared. And then again to write dy, capital D small t and y of x inside the square bracket. So remember, you have to write y of x because y is the unknown. Double equals to 0 and give a comma and write the unknown, which is y of x, and then give a comma and write the parameter x. We have 3 solutions this time, and we'll get 5 curves from each of the solutions. So in total we'll have 15 curves in our graph. This time the output cell number is 1, so let's retrieve this output. So y of x will be replaced with output 1, so %1. So the output cell number is 1, so we write %1, and again we'll replace C1 with alphabet A, small a, and let's set a variable sol, and then we will plot this. So write plot, and again inside plot write evaluate, and then write table, and inside the table we'll write the sol, and let's take a from -2 to 2 and x from -5 to 5. This is the same expression I used in the last problem. So these are our 15 curves here. You can use plot legends here, but it will get a bit messy. Let's see. So there are 15 curves, so it's hard to tell which one is which. So let's not use plot legends here. It's not useful. We can change the range of x a bit, I think. Let's just take smaller range of x to get a clearer view of what's happening. Let's take x from -3 to 3. I think that's fine. So that's all for this video.